pleasure to introduce Ken de Kommer from the Free University of Brussels, who will lead off with the talk on the equivariant correspondences.
Thank you, Richard, and thanks to the organizers for the opportunity to give a talk here. So this will be about joint work with my PhD student. So we heard already a little bit about correspondences in previous talks. So basically, the most simple version of a correspondence that we can think of is just a bimodule. So we have an algebra A and algebra B, and we look at bimodules. But I'm interested in equivariant bimodules, so it means we also have some symmetry. For me, it's a bottom symmetry. So we think of a Hopf algebra or even just a bialgebra, which has some comodular structure on this vector space. But then we want compatibility with the bimodule structure. So basically, what we ask is that there's an action of H on A, there's an action of H on B, and then the comodular structure for H on this one is compatible with the action of H on A and B. So this is very roughly the structure that we are interested in, but you can look at this in various settings. So you can be just pure algebra, or you can be in C-star algebra setting and look at Hilbert modules or Hilbert bimodules. We will be interested in von Neumann algebra setting, so we will be looking at correspondences in the sense of con. Okay, so because I didn't want to assume that everybody knew von Neumann algebras, but sometimes at these conferences it's mainly C-star oriented, so I just have a small preparatory slide saying some things about von Neumann algebras. Basically, one of the most famous theorems is that von Neumann algebras are C-star algebras, which in a way have both an algebraic flavor and an analytic flavor. They have an algebraic flavor because they can be characterized as those, let's say, complete C-star algebras which are equal to their bicommutant. So if we take any element, if we take the algebra of operators commuting with A, then the commutant of that algebra is again the same algebra as you begin with. This is the bicommutant von Neumann theorem. Or there's an analytic characterization. You can say, well, it's a C-star algebra for which there exists a special subspace of its dual, so that A is actually characterized as a dual of the subspace of its dual. So this is an analytic characterization, and both viewpoints are very useful and allow to have a very flexible theory. And so if we view complete von Neumann algebras, like in the first point, we often call them von Neumann algebras. If we view them abstractly, as in the second point, we sometimes call them W-star algebras, but nowadays the distinction is not really made anymore, so I will freely switch between these terminologies whenever I feel like it. So examples that you can think of, if you're not familiar with von Neumann algebras, well, we saw some very interesting von Neumann algebras this morning, but they're a bit too complicated maybe for this talk. Really, you can just think of all operators on a Hilbert space. Think of small L infinity of some discrete set I, L infinity of some well-behaved measure space, or what is particularly relevant for this talk, the group von Neumann algebra. So basically, you look at translations on L2G, and you look at the bicommutant of the set of translations. And this will be the group von Neumann algebra of your locally compact group G. Now, because of this characterization that A is basically the dual of some other Banach space, there's some natural topology which is coarser than the norm topology. So this is the W-star topology, and this is usually the kind of topology you want to consider in von Neumann algebras. So for example, if we have linear maps between two von Neumann algebras, we'll say that it's normal if it preserves or if it's continuous with respect to this weak star topology. So as I said, we'll be interested in looking at bimodules over von Neumann algebras. And so because von Neumann algebras live on Hilbert spaces, our bimodules will basically be Hilbert spaces. So we'll say that a correspondence in the sense of con, and this notion was also in a way popularized by Soren Poppa. So a correspondence from von Neumann algebra A to von Neumann algebra B is simply a Hilbert space, which is a bimodule over A and B, in a way which makes sense for operating. So we say that we have a representation of A, which is normal, in the sense I explained, by normal star homomorphisms. We have some anti-representation, or what is the same thing, representation of the opposite star algebra B on B of H, and we ask that these two things commute. So this is really what you would directly think of as a bimodule in the operator algebraic setting. So, for example, there's one very famous construction, which is basically the an offshoot of Tobita-Takezaki theory, is that to any von Neumann algebra, you actually can associate the standard Hilbert space L2A. And so it's some canonical Hilbert space which you can attach to any von Neumann algebra, and we call this the identity correspondence. So you see it as a correspondence from A to A. I'll explain in a moment why it's called identity correspondence. But it's something you get for free in a canonical way. And starting from this identity correspondence, we can construct many more correspondences, because if we have just an inclusion of von Neumann algebras, well, we can take this one here for B and just restrict one of the legs. So we can look at an AB correspondence by restricting the BB correspondence L to B, one of the legs to A on the left, or on the left as well as on the right, then we get an AA correspondence. Okay. So this is a very rich, very easy, but a very rich source of correspondences which are worth and interesting to study. And going a bit beyond this notion of having an inclusion of von Neumann algebras, you can also look at, let's say, normal unital completely positive maps. There's some variant of the Stein-Spring construction, and you get also from this an AB correspondence. So instead of morphisms, you can also look at more general things like UCT maps, and you still get correspondences from that. Okay, so that's a very flexible theory, a very well-working theory, but we will be interested in equivariant stuff, so we need to know what are our quantum symmetries. And because we work in operator algebraic setting, we work with locally compact quantum groups. So this can get quite technical if you're really want to learn the basic theory of locally compact quantum groups. But it's the same as with Tobita-Takezaki theory. Like, once you get through the basics of it, or once you master the abstract theory behind it, then it becomes very smooth and very easy to work with, and it's basically purely algebraic. And the same thing is with locally compact quantum groups. Even though there's a very rich and very technical machinery behind it, once you have set this up, it's very smooth to work with in a way. So I hope that this talk will convey that I won't be using very much technical machinery, and the things are very intuitive in a way. So let me just briefly go over the definition of what a locally compact quantum group is. So it is a von Neumann algebra M, and it should behave like a Hopf algebra, so we need at least a coproduct. So we have star homomorphism, which is normal from M into tensor product of M with itself, satisfying co-associativity. So this much is easy and clear. The problem is, however, that if we want to look at the operator algebraic version of the other things that make up a Hopf algebra, like the antipode, then we're in trouble, because the antipode turns out to be something which is horrible from the operator algebraic viewpoint. So instead of trying to immediately go to how to construct an antipode, we take a different route, and instead we say, well, if we want this to be a version of a locally compact, a quantum version of a locally compact group, maybe it's good to have Haar measures around. Yeah? So it turns out that this is actually sufficient. So we just ask that this von Neumann algebra M with its coproduct, that it has some natural weights. So I won't go much into details about what weights are, but you just think of them as kind of like a generalized notion of integral. To any positive element in M, you can associate some number 0 with infinity included, and then saying that their Haar weights is basically saying that if you shift a function from the left or right, and you integrate with respect to the respective Haar measure, then you've basically just integrated the original function. And so this is just expressed in formulas in this way, and that's a very easy way to write it down, but then you need a lot of theory to show that this is actually sufficient, and gives you a very rich theory, which was developed by Westermans and Baas at the beginning of 2000. So examples, if you've never seen locally compact quantum groups, for the rest of the talk, you can really just think about an infinity of G for G a locally compact group. And then the coproduct is really just implementing the product on the group. And these weights, they're really just integrating with respect to left or right Haar measure. Now, at some point, I will also refer to duality for locally compact quantum groups. Then you can think of passing from L infinity of G to the group von Neumann algebra, which I introduced a moment ago. Okay, so this turns out to be also a locally compact quantum group. Now the multiplication of the group is encoded on the algebra level because we took here translation operators, so they multiply according to the group draw. But now the coproduct is kind of trivial, it's just diagonal on the generator's lambda G. So these are the main examples of locally compact quantum groups that you can think of for the rest of the talk. I will give some more examples later, but really, if you haven't seen them before yet, it's a bit hard to form a good idea of them, so just keep these things in mind. Okay, so now if we want to go beyond the basics, if we think of groups, well, we think of representations, we think of actions. So it turns out that these things can be very naturally formulated also for locally compact quantum groups. So a unitary representation of a locally compact quantum group is simply a unitary V of H for some Hilbert space H tensor the associated von Neumann algebra M, satisfying this kind of co-representation formula, which is well known from algebra theory. And that's it. That's all you ask. This together with the fact that it's unitary, that's sufficient. And if your G happened to be an ordinary locally compact group and your M was an infinity of G, then this is really just a notion of unitary representation of G as you know it. Same thing for an action. So if we have a von Neumann algebra A, then we say that an action of our locally compact quantum group G and A is simply what is known in algebra language as a coaction. You have some homomorphism from A into A tensor M, satisfying the coaction property. And again, when I feel like it, sometimes I will also refer to this as a G-dynamical von Neumann algebra, a von Neumann algebra with dynamics governed by G. And that's it. I don't ask anything else. And it turns out that this is already sufficient to have, for example, a link between actions and representations, because there's a theorem of Stefan Bass generalizing work that Hausdorff had done for classical locally compact groups. So Bass has shown that whenever you have an action on a von Neumann algebra, you can always implement it canonically by a unitary representation on the standard Hilbert space associated to A. So again, if I have an action on IA like this, there always exists a canonical unitary UA on L2A, such that alpha A is really implemented by this co-representation. So this is a very nice interplay between the theory of actions and the theory of G representations. Okay. So one example to keep in mind, well, we always have one canonical action from the start. If we have a von Neumann algebra, if we have a locally compact quantum group, we have an associated von Neumann algebra M, and just by means of the coproduct, this will be actually an action of G on itself. This is just the usual translation action. And so the canonical implementation here, I will call it the right regular representation. It's the analog of the right regular representation for the locally compact group. So this is one particular case of this construction, but this one here you actually start the theory of locally compact quantum groups building this. So it's not like you use the general theory to construct it, but it's just an example in my presentation. Okay, so now we have correspondences for von Neumann algebras. Now we have our quantum symmetries, they're locally compact quantum groups. Now we can bring both things together and look at equivariant correspondences. So there's one extra piece of information. So I said in the beginning, well, the antipode for locally compact quantum groups, it's a bit horrible. It's an unbounded operator. But it turns out that in operator algebraic framework, your quantum groups, you can always decompose the antipode into some unbounded part and some bounded part. And the bounded part is what is called unitary antipode. And this is much nicer. This is just an anti-star homomorphism from M to itself. So anti-homomorphism, it means you change the products when you multiply after composing with R. And it's also anti-co-multiplicative, so if you compose R with the coproduct, you change the legs for the coproduct. So this is a structure which, in some sense, can replace the antipode, although you have to replace it in a good way. But in any case, it allows us to construct now equivariant correspondences. So this definition appeared explicitly, as far as I know, first in a paper of Rano-Skalski, a very recent paper. They only looked at compact quantum groups, and actually their actions were on C-star algebras, but the definition is exactly the same as is there. So you can just immediately extend it to the von Neumann algebraic setting, and it's really the right notion that you want to have. So what do we want? Well, remember, we wanted to have bimodules, and we wanted to have an action over quantum symmetry. So the same here. You take a Hilbert space. So we have two von Neumann algebras A, B, which have both an action by G. Then I'll say that the G equivariant correspondence is a Hilbert space H, which is at the same time an AB correspondence, and which also carries a unitary G representation. So these are my two components, and now I have to let them speak to each other, so I have to have compatibility relations, and they're simply expressed by saying that U has to implement alpha, and U star has to implement my action on B. And just because of things having to work out, you need this unitary antipode here because you want the map here to be an anti-representation of B, so you want something which is anti-multiplicative. And so that's all the things you need. This is your operator algebraic version of an equivariant bimodule. And so we also saw a little bit of category theory already. We saw some things about C-star categories. So here I will talk about W-star categories because, well, if I look at the class of all these equivariant correspondences, well, they're Hilbert spaces. So I can look at operators between Hilbert spaces which preserve all the structure that we have in it. So they have to commute with the action of A, they have to commute with the action of B, and they have to commute with the representation of G. And because of the particular nature of intertwining relations, we can actually think of this thing as a categorification of a W star algebra or von Neumann algebra. So the morphism spaces in this category, they will be kind of like von Neumann algebra behaving. And what is more, as you would expect from what you know from bimodules, well, we have natural composition of bimodules by balanced tensor products. So also here, we can actually complete this do this in a global way as a W star bicategory. So we saw some notions about bicategories yesterday. So W star bicategory because we can compose correspondences by what is known as the confusion. So if we have an AB correspondence H and a BC correspondence G, there's a particular way to form a tensor product over B. So what I end up with is an AC correspondence. The actual construction can be a bit technical. There's various ways to look at it. But for this talk, you can just think of it as an ordinary tensor product between bimodules. I won't get into the technicalities. But of course, I also need to have a representation of G on this thing. And here I just take the diagonal representation. So that means I take the representation of H, I take the representation of G, and I just multiply them. And then you have to show that that makes sense, and that is actually a well-behaved operation on this contensor product, but that turns out to be fine. Okay? And so then you go through the motions and you show that these things are compatible and that you get in a good way a bicategory. Okay, so let me look at some examples. So first I'll look at some general constructions of which equivariant correspondences might be interesting to look at, and then I'll give you some particular contexts in which equivariant correspondences appear. So first, some general constructions. Well, I told you there's a identity correspondence. Well, if we have a G-dynamical von Neumann algebra, it's of course the fact is of course that the trivial correspondence will indeed be an equivariant correspondence, because we already saw that by Va's theorem there is a canonical representation U which will implement the action of G on A. So the identity correspondence of A to itself is equivariant with respect to the implementing unit. So this is just the basic object. It's the identity. Why is it called the identity? Because with respect to this tensor product, it will actually act as the identity. If I tensor with the identity correspondence, it's isomorphic to the thing I start with. Some more interesting examples. So these terminologies, so I should say that this is still work in progress, so we haven't completely decided yet on the best terminology for the objects that we consider, but for now we have called them G semi-coarse GAA correspondence. So what do? So we look at a G equivariant from algebra A. We look at L2A tensor L2 of M, and doing the algebra for the quantum group. And then we will basically look at it as a bimodule over alpha A. So alpha A lives in A tensor M, so it will act on the left on A tensor, on L2A tensor L2M, and it will act on the right on L2A tensor L2M. And then with this regular right representation that I introduced before, you can show that this is actually going to be an equivariant AA correspondence. So why do I call it the G semi-coarse correspondence? Well, I can always simplify by either taking A, the trivial algebra C, then I will end up in representations of locally compact quantum groups, or I can say I take G trivial, and then I will end up in the theory of correspondences. So if I take here A trivial, then I just have L2G with the representation, right regular representation. Okay? So it means that this is the regular representation when A is trivial. On the other hand, when G is trivial, then this will just be the identity correspondence for A. This part disappears, and I just get L2A with A acting on the left and the right. So now we can reverse the roles of A and G. So instead of saying I want G to be acting regularly and A to be acting trivially, I will say, well, A has to act non-trivially. So basically this means that I will let, so I look not at AA but at AB correspondences. I take L2A, just ordinary Hilbert space tensor product L2B, and I view this as a left A module by A acting on L2A, and a right B module by B acting on L2B. So this is very easily checked to be correspondence. And now you make it into a G equivariant correspondence by just taking the tensor product of the representations, canonical representations on A and B. So again, just using basic algebraic compatibilities that you get from the theory of locally compact quantum groups, you can quite easily check that this is indeed a well-defined equivariant correspondence. And indeed, when now G is trivial, we get a coarse AB correspondence. And when A and B are trivial, we get a trivial G representation because then this is just C with the trivial representation. So these two are kind of like opposites of each other. But we can also combine them together and have both regular representation for G and regular or coarse representation for the bimodule. So this is the last example in this general framework. So now we take, basically, we smash them together. We take A, tensor M, tensor B. A acts here, B acts here, and then we take the tensor product of implementing representation here, regular representation here, and so at the end, I'll say a little bit about what role these correspondences play in the general theory of why we are interested in them. But for now, I just present them to you as some general examples that you can make in the theory. So now I want to move on to some concrete contexts where we see these equivariant correspondences play an important role. So the first class of examples, comes from the work of Luciano and Stefan Vaas. So basically, I present a simplified setup. So you can just think of having a locally compact, totally disconnected group and two compact open subgroups, K1 and K2. So because they're compact open, the coset space will be discrete. But it carries an action by G, if I write multiplication here. So we have an action of G on a discrete set, and then just by putting it in the framework that we have considered before, we can look at equivariant correspondences. So we have this gamma 1, we make L infinity of it. This is a von Neumann algebra, as I told you in the beginning. Same for gamma 2, if I divide that by the second compact open subgroup, I get L infinity of gamma 2. They have actions by G, and so I can look at G equivariant correspondences between L infinity of gamma 1 and L infinity of gamma Now, the particular nature of this setup makes it that these categories are extra nicely behaved. They're basically discrete categories in the sense that any object you can just decompose into symbols. So it's kind of like some semi-simplicity condition. So I won't explain the formulation I give here, but basically this rigidity means that if I look at a nice subclass of the correspondence, basically the ones for which so I have an action of L infinity gamma 1 on my Hilbert space. That just means I have a gamma 1 grading of my Hilbert space. And when I put this finite here, I'm just asking that the components of this grading, they're finite dimensional. And the same thing for the action of L infinity of gamma 2 from the right. If I here look at all the graded spaces, they also have to be finite dimensional. Yes?
I'm just wondering exactly what you mean by a W star bicategory. So is there an involution on the 2 cells or also on the 1 cells?
So there's an involution on the 2 cells. Here you also have an involution on the 2 cells. So I will come to this. There's an opposite correspondence you can make. Yeah? But I'm just using this as a kind of general formalism to briefly say the kind of structures that are involved. But yes, you do have opposites both on the 2 cells and 1 cells.
Also on the 1 cells?
Yes. So I'll say it in a moment for the opposite. Yeah. But so, just to say, in this particular case, the W star categories that you get, they're very easy to understand. They're basically just blocks that you put together, and they're basically just matrix algebras, the morphism spaces. But the reason why I bring up this example is because recently, Stefan Vaz, with a student of his, they turned this philosophy around to actually construct quantum automorphism groups. So, just to frame the construction that I made before differently, so let's say that we look at a graph now, gamma, which is locally finite, so each node just has a finite number of edges leaving. Let's say I also choose some roots, and this is important. And I assume that it's vertex transitive, so it's homogeneous enough. I can find for any 2 nodes, for any 2 vertices, some automorphism moving one vertex to the other. I don't really need this extra assumption, it's just to make things nice to formulate. But in this case, I do get a totally disconnected locally compact group, just looking at the automorphisms of my graph gamma. Then I can look at the compact subgroup fixing my root. And because of my vertex transitivity, my quotient space of G with this compact subgroup will be exactly the vertex set of my graph. Okay, so I'm basically in the setting of Arano Vaz of the previous slide. And now what Rollier and Vaz did is they basically showed that there exists for this graph a quantum automorphism group, so a locally compact quantum group acting on my vertex set such that it can be interpreted as the quantum automorphism group of this graph. So again, I will not really enter into detail because this will not be a talk about this construction, but basically what they do is, well, you already know from the previous slide that we have an interesting discrete kind of category that we can consider by looking at L infinity of the vertex set on which our quantum automorphism group should act. So we could look at equivariant correspondences. I think so, yes. I thought I had implied it. No, it didn't imply it. Yes, I wanted connected, yeah. But you can go beyond it, but it's, yeah. So I wanted connected. Thank you, Christian. So, so the point is, you expect from the previous slide that this will be a discrete category. Now, the point is that Rollier and Vaz, via graph theoretic techniques, they actually find a different model for this category, show that this category is indeed a discrete category and that it is rigid, and then basically starting from this, they are able to reverse engineer and show that the object here exists and is a locally compact quantum group. So it's a bit vague the way I explain it here, but really the philosophy is that we try to put what we know from the classical world in the quantum world and use it as the soil for the construction of some very interesting locally compact quantum groups. Okay, so this is one class of examples why that recently came up and it turned out to be very interesting. Another class that I wanted to emphasize a little bit is some work that I did with my other PhD student, Joel Zokutala. So here we basically look at compact quantum groups, and we look at their group von Neumann algebras. Now, I want to look at von Neumann subalgebras, which I think of being compact subgroups, but the tricky thing is that they're only one-sided quantum subgroups in a way. So if I have this von Neumann subalgebra of LU, and I apply the co-product, I do not end up in LK tensor LK, but only in LK tensor LU. But this turns out to be sufficient for most of the theory. So for example, you still have some kind of dual object, some quotients, some coset space that you can construct, which I will denote O of U mod Q mod K. So because I'm in the compact setting, instead of just working with von Neumann algebras, I also have purely algebraic objects. So there's some associated, nicely behaved star algebra of associated to kind of like a quantum homogeneous space, dual to the co-ideal I made here. And then it turns out that, so by this, you see that there's actually a coaction of LU on LK. So I can look at equivariant correspondences. And in this setting, these equivariant correspondences, they can be somehow simplified. So instead of saying I have to have an LK bimodule with an action of LU, I actually only need to have a representation of the coset space, or the coset space algebra, and a representation of my compact subgroup K. So you can show that there's an equivalence of categories between these two things. But what is really surprising is that somehow this category here, as I explained, it has a natural tensor product. Correspondences can be multiplied. Whereas here, there is no obvious way, if you have a representation of this guy, to multiply it with another representation of that kind. Okay, so it's somehow very surprising that by means of this identification, you obtain a tensor product here. And so the reason why we are interested in these specific classes is that they allow a way to quantize real semi-simple groups. So far we only worked this out for the rank 1 case, but the construction is really very general. You can do it in any rank. And any
the identification of the categories equivalence or isomorphism?
No, it's an equivalence. Yeah, so yeah, it's some kind of Morita equivalence that you implement it with. Yeah, so it's really an equivalence, not an isomorphism. Hilbert spaces change when you move between one and the other.
It's not so surprising that one side you have tensor, the other you don't.
Yeah, but still. Yeah. So the specific examples that we are interested in is coming from a quantization of a real semi-simple Lie groups. So I'll just give it as a brief statement that there's some, you saw this last week if you attended the school, there's some quantum group called the ZQ2. It happens to have some compact quantum subgroup SOQ2, which is not a real compact quantum subgroup, only a co-ideal in this sense. But that's enough to do this construction. And then it turns out that this representation category, you can actually consider it as a representation category of some kind of quantum SL2R. And so we were very happy when we figured out this correspondence because it allowed us to somehow compute tensor products of quantum SL2R representations, which were a priori not clear from this description. Okay, so I went a bit fast on these examples, but I just wanted to show them to you to kind of show that these are very recent structures, very recent concrete examples which are considered, which is kind of the motivation why we wanted to develop a general theory concerning these equivariant correspondences. So now I will return to the general theory. I told you in the beginning I was going to say something about dualities. So any locally compact quantum group, it will have a dual locally compact quantum group. So if you think of the classical theory of locally compact abelian groups, this will really just be the construction of the Pontryagin dual locally compact group. So I start with my compact quantum group, my locally compact quantum group G, and I construct some other von Neumann algebra M hat, which whose associated Hilbert space I can actually identify with the original L2 of the original von Neumann algebra M. And this one, I will, if I view my M as being like an infinity functions on my locally compact quantum group, I will view M hat as the associated von Neumann algebra. So this is the kind of intuition that you can keep in mind when considering this kind of duality. And it turns out that this kind of dual construction, you can also do it for actions. So if I have a G-dynamical von Neumann algebra A, I can make a cross product construction. And this cross product, it will have an action by the dual locally compact quantum group. So I kind of view this cross product as kind of like a dual of A. I only use this term, this notation during this talk because it's not completely perfect, but just think of it as being some kind of dual of A. And now, if I have an equivariant correspondence, I can also take a dual of that. So, if I have an GAB correspondence H, I can kind of take a cross product with G. I get a new A hat B hat correspondence, which is equivariant with respect to G hat. So I won't explain the whole construction here, but just think of this as kind of like a generalized duality that you have for equivariant correspondences. And it turns out that this actually gives you an equivalence of W star by categories. Again, I won't give all the details about what this means, but you basically have an equivalence between G equivariant correspondences and G hat equivariant correspondences by sending A to its cross product and an equivariant correspondence to its cross product. And the only thing that I want to emphasize here is that why is this an equivalence of by categories? It respects composition. So if I take the composition of two equivariant correspondences and I take the dual, then that's the same as first taking the duals and then the composition. So that's one thing. The other thing is that it's involutive. So this is what is called the Takazaki-Takai duality. So if you take A, you take its cross product. Well, it has an action by G hat, so you can take it again a cross product now with G hat. This construction here, it's basically involutive, so the dual of the dual is G itself. So it means the cross product of the cross product, it has an action by G. And then it turns out that if you do this construction twice, the object that you get is basically Morita equivalent with the original object, which means, in a way, that here needs an equivalence of So it's quite nice that you have this general framework in which you can consider this kind of duality. And what we will now do is, so this was basically all the algebraic stuff. So this is all the constructions you can do on the algebraic level, but because we work with normed algebras and we like approximation properties, we now want to look at, well, is there a nice way to construct some topology on sets of correspondences? Okay, so this is basically what I want to do now. I want to construct a kind of Feld topology on correspondences. So first, a small thing I note is that if I have a G representation, so this was some unitary U living in V of H tensor M, then if I consider the pre-dual of M, this has a product just by convolution, so omega star chi for omega and chi functionals is just omega tensor chi composed with delta. So if I have a unitary G representation, I get a representation of this Banach algebra just by this formula, just by slicing with omega in the second. And now I can say that if I have two correspondences, so over the same von Neumann algebra, so I have a GAB correspondence H and a GAB correspondence H prime, I can say that H prime is close to H if I can somehow approximate finite parts of it with finite parts of the other one. So that's a very rough description, so I wanted to write at least this definition out. So what it means is that, well, we have some epsilon and some finite sets in A, B, with the dual of M and H. So the finite subset of H I note xi1 up to xin, such that there exists xi y prime also in H prime, actually in some finite amplification of H prime, such that the norm of the new vectors psi I prime does not exceed the norm of the original vectors psi I, and such that if I take matrix coefficients of compositions, I let A act, I let omega act, I let B act, and I take the matrix coefficient at psi I, psi j. This should be almost the same as doing the same thing in the representation H prime with respect to the vectors psi I prime. So these matrix coefficients have to be epsilon close to these matrix coefficients. So one thing that is important and that's somehow was not obvious in the beginning is that the order of the factors turns out to be quite important. So the fact that you have to put the representation of the group in the middle, you would think, well, I could place it anywhere, and it turns out not to be correct. So it turns out that if I put it at the end and I put pi A rho B, then you don't get what you want. On the other hand, if I change A and B, this doesn't matter, because we expect some kind of symmetry between A and B. But somehow what got the theory rolling was the realization that if we put them in this order, this is what actually makes things work. And for example, one result that is coming from this is that you can really see. So one thing is that there is a C-star algebra which governs the class of G, AB correspondences. So there's some kind of universal C-star algebra such that any GAB correspondence lifts to a representation of this C-star algebra. So not every representation of the C-star algebra will be an invariant correspondence, but at least any correspondence can uniquely be lifted to a representation of this one. And with the topology that I introduced in the previous slide, it turns out that it really coincides with what is usually known as the Pell topology on the representations of this C-star algebra. So that means you're in business, because now you can just apply results that you know for usual Pell topology of C-star algebras to this kind of category. One thing I should say is that this C-star algebra, you should kind of think of it as kind of like a double cross product. So it has A, it has B, and it has the convolution algebra of G. Now, in the algebraic landscape, such double cross products, they were also considered. Actually, they were considered in some papers of Moscovici and Kohn, and also in some paper of Nikšić and Weiderman in purely algebraic context. And then, again, in C-star algebra landscape, they were considered by Arano and Skalski, but for G compact. And so we kind of have a version in von Neumann algebra land of this kind of double cross product, but it's a bit tricky because we have von Neumann algebras mixed with C-star algebras. But it turns out to work, and it turns out to give you nice correspondence between these two categories. One tricky thing which I just wanted to mention is that I told you, well, it's kind of like a double cross product with A, B in convolution algebra inside. But it's not that straightforward, because actually you can't embed A and B directly inside the C-star algebra, and not even in its multiplier algebra. So it's kind of like some weird construction that you have to make from the C-star algebra here, which is classical, but which is somehow not used that much, which is called a set of quasi-multipliers. So it's basically all those elements such that if I both multiply from the left and right at the same time with some element in C, then I land in C. But it's not sufficient to just touch it from the right or just touch it from the left. I need to do it from both sides at once to land in C. So in particular, it's not even an algebra, this thing. But you can still work with it, and it turns out to behave nicely enough so that you can build a nice theory. So coming back to this question of having these opposites of correspondences. So this is already known from the theory of just non-equivariant correspondences, that you kind of like have a dual for one cell, so you have a dual for correspondences just by looking at the complex conjugate Hilbert space, and then using just by the canonical anti-isometry, anti-unitary from H to H bar, you can just flip the action of B and A. And there's also a way to then take the complex conjugate representation of G on this one. So this construction is very easy, very formal in a way. But it turns out that it gives you a right, well, it gives you some notion of an opposite of a one cell. And it turns out that all the constructions that I considered this far, they are actually continuous with respect to the topology that I introduced, this felt topology. So if I have some net correspondences approximating a correspondence, and also the duals will converge in the same way. If I multiply with a fixed correspondence on the right or on the left, then also if H alpha goes to H, and H alpha cross G will go to H cross G. And the same thing for the duality that I introduced. So if I have G correspondences converging, then also their duals will converge. And so what makes this work is simply that this felt topology looks kind of complicated, but it can be captured by a much easier notion, the one of weak containment. So this is just something coming from C-star algebra theory. So if we have two representations of a C-star algebra, let's say CGAB is our C-star algebra, then G will be weakly contained in H if the representation on G will factor through the representation on H. Okay, so I can, instead of going from C to B of G, I can first go from C to B of H, and then from the image in B of H go to B of G. So that's the notion of weak containment, and it turns out that this notion is basically giving you the same information as your felt topology. So we can show that some correspondence between these equivariant correspondences, it will actually be felt continuous if and only if it preserves the weak containment, as long as you make sure that it satisfies, that it preserves these not just direct sums, but arbitrary and infinity direct sums. So this is a notion that we also saw in the talk yesterday, that analytic setting, it's natural to somehow not just restrict to preserving direct sums, but preserving. And then just using this correspondence, this makes it a bit easier, or gives you some more flexibility to check that these operations are all continuous. So I want to end with some relations to amenability considerations. So I want to recall some recent results due to Bannon, Marachi, and Ozawa, which completed some work that Claire and Roche had started, and which is basically based on the breakthrough results already from Alain Kohn concerning equivalence between semi-discreteness and injectivity of von Neumann algebras. So basically, the result that they have obtained is a kind of relative version of that result of Alain Kohn. So basically, they showed that if you have an inclusion of von Neumann algebras, so this is not equivariant, this is just purely in a setting of correspondences. So if you have an inclusion, unital inclusion of von Neumann algebras A and B, then the identity correspondence for A will be weakly contained in the A correspondence L to B, if and only if there exists some, this equivariant shouldn't be there. If and only if there exists some conditional expectation from B to A. So just some UCP map from B to A, which is the identity of A. So this direction from here to here, this is not so hard. It's the way back that is usually very hard. But so we obtained partly a generalization of the easy direction in the equivariant setting. So we showed that if we have an equivariant inclusion of von Neumann algebras, then the identity correspondence is weakly contained, or equivariantly weakly contained in AA correspondence L to B. That implies that there exists an equivariant conditional expectation from B to A. At the moment, there's no real hope of obtaining the converse direction because there is a well-known open problem in locally compact quantum group theory asking equivalence between amenability of G and co-amenability of its dual. And this is basically, if you can solve this in general, then you would obtain that particular result as a special case. So at the moment, I don't really have any hope of finding the the inverse direction. But at least one way can be done in this general setting. And at least for some particular cases, it turns out that we can find the way back, although really this is just a reformulation in a way of a result of Bearden and Kram that was obtained recently. So here, I don't look at quantum groups, I really just look at locally compact groups. And then we look at a very particular inclusion of G-equivariant von Neumann algebras, namely, I start with the von Neumann algebra A, which is an action of G. And then I look at B being the tensor product of A and an infinity of G. And depending on how you set things up, let's say that we act by right translation of an infinity of G. And then with this particular case of B and with G being classical, you can in fact show that the equivalence holds, so that this one is weakly contained in this one, if and only if there exists an equivariant conditional expectation from the tensor product. So at least we were happy that in this case we could obtain the equivalence, but really the hard work was done in this paper by Bearden. So let me end with some general formalism that I want to introduce concerning amenability. So this whole thing was kind of started because of the examples that we had. So in particular, these quantizations of real semi-simple E groups, we wanted to kind of see, well, can we say some things about approximation properties for these? So property T, Heuer property, this kind of stuff. But then once we looked at a very general setting here, we kind of mainly stuck for the moment to amenability. So there's a notion of amenability you can introduce in the setting of correspondences that was made explicit by Claire Anatole de la Roche. So basically she says that the usual correspondence is left amenable if and only if the identity correspondence is weakly contained in a tensor product, a confusion product of H and its dual. So if you would be considering compact groups and representations, well, then you would know if I take a representation and a tensor with its contragradient, well, the identity correspondence, the identity representation is actually contained in this tensor product. If you go beyond compact groups, you can't expect this, and you can't even expect a weaker form of containment. You can't even expect in general this weak containment property. But if it holds, then you have this kind of amenability phenomenon. So this definition, you can just immediately plug it in the equivariant setting. So let's say that some equivariant correspondence is strongly left amenable, or equivariantly strongly left amenable, if the identity correspondence is equivariantly weakly contained in the tensor product of the correspondence H with its opposite. So some examples of this kind of tensor product, linking back to the examples we saw in the beginning. So if we have a restriction of, so we have an inclusion of A and B, and we restrict L to B on both sides to A, well, that's basically taking a contensor product of L2 as an AP module with its opposite. You somehow kill B in the middle, and all you obtain is the A bimodule structure. As a particular case, actually, this G semi-coarse correspondence, it's also of this form, where you just amplify the action of alpha A on the right to A times N, and that's just this particular case of this case here. And also the coarse correspondence, you can also see it as this kind of confusion product, where now I just take the coarse correspondence between A and M, and I take its tensor product with its opposite. So some of these constructions that I made in the beginning, they are exactly of this form. And so saying that my identity correspondence is weakly contained in this one of this one is actually saying that this H, which I get here, would be a strongly left amenable correspondence. So there's one extra correspondence which I put on the top of the slides, which I won't say much about. There's one extra example which is called the adjoint correspondence. So now we kind of like have an intermediate A acting on the first leg on the left, with alpha A acting on the right. And then we have to take tensor product of representation here with some kind of adjoint representation here. I won't go into details. I just want to formulate that this helps us in finding some good dualities between approximation property for correspondence and approximation property for dual correspondence. So let's say that if we have an action of locally compact quantum G from algebra A, let's say it's strongly G amenable if the identity correspondence is equivariantly weakly contained in this G semi-coarse correspondence S. Let's say we have some strongly energy amenable action if this identity correspondence is contained in this adjoint amplification. And let's say that it's GW star amenable if it's weakly contained in the coarsest correspondence. So this you should really think of as what is corresponding to usual amenability of actions of groups on von Neumann algebras. But as this is something new that we hope to elaborate on in future work and show some interesting examples. But so far we don't really have much examples of this thing, but we expect there to be many interesting examples. But anyway, we just have a general theorem relating this kind of approximation property for the dual action. So for example, we have that A will be strongly G amenable, so the action of G on A will be strongly amenable, if and only if the action of the dual of G on the cross product of A and G is strongly inner amenable. So we kind of have this switch between strong amenability and strong inner amenability, because also conversely, if we start with something strongly inner amenable, then the dual is just strongly amenable. And the last one, the GW star amenability, this is kind of like a self-dual thing. So we have that A is GW star amenable, even though we this dual strongly GW star amenable. So this is basically where I wanted to stop. So thank you.
Certainly have time for some questions or comments.
In this correspondence setting, if I pass it from a small locally compact quantum group G to a larger one, is there a notion of extending such construction that generalizes the induced representation?
So I should have said that actually, so there is some paper of Stefan Vaas on induction for locally compact quantum, and he uses this kind of formalism. I should have said that that was also one area where these equivariant correspondences were actually already introduced in a way, for this particular case of inclusion of quantum groups, yes. But we didn't really consider induction in a very direct way yet in this framework.
Just a comment. I mean, since the first talk today was slightly related to Cartan's property too. Is there an analog for property two?
Yeah. Yes. So
which is the opposite of amenability.
Yes. So the fact that we have this Feld topology, we can say identity correspondence is isolated. And we do have examples that we think will satisfy this coming from these quantizations of real semi-simply groups. So, but it's not done yet. So that's for the next talk.
Other questions? Yes, please.
Do you have a notion of CP or ZB multipliers?
You mean equivariant? Well, no, it's kind of annoying. So actually, I have one extra slide. So the point is that if you want to formulate these kind of approximation properties in terms of actual Hilbert correspondences, you kind of have to introduce your coaction on your correspondence. So you would like to see yi star yi as implementing your UCP map, but at least in the formulation that we have here, we have to apply coaction to one part and not to the other, so we can't just formulate it in terms of the event operation y star y. We're looking at it in the context of compact quantum groups as a separate follow-up project, and there things are a bit more amenable to formulate it in terms of multipliers. So we're working on something like that.
If there are no further questions, then let's thank Kenny again.